here we come across hypothesis testing. So the important thing right at the start of hypothesis testing is to always keep in mind that we're applying our existing knowledge. All right, so there's nothing new here. There's no new knowledge here. It's the way that we're applying it that's new. You know, when we were dealing with estimation, we would measure an x-bar, a sample mean, which we could observe, and then we'd stick a confidence interval around that. This is the previous module. We'd say, well, we're 95% confident that the true mu lives somewhere in this range, okay? With hypothesis testing, what happens is that we hypothesize that we know, it's that word hypothesis, we hypothesize that we know where mu lives, all right? So it's called mu naught. That's a hypothesized value for the mean. All right, so we hypothesize something about the mean. We might say we know where it lives, or we might say that it's certainly not greater than a certain level or something like that, right? So we know something about the true population, or at least we claim we do. That's what a hypothesis is. It is a claim. And what you do then is you take a sample, all right? So you might see a sample mean over here. And the idea is that if that sample mean is very unlikely under null conditions, it's quite, is that a big distance away? Well, that's where our z values and t values come in that we've already met. If that distance is too far away, then we would reject the hypothesis that mu is here. All right, that's the general idea. And these two are linked because you could say, one thing you could say is if you do a confidence interval, if you perform a calculation of a confidence interval, like we did in the previous module, and you create that confidence interval, just like we did in the previous module, if you hypothesize that mu was in that confidence interval, you would fail to reject that statement. All right. However, if you assumed or hypothesized that mu was outside that interval, then you would actually reject the hypothesis, all right, because it's too far away. However, the direction of travel is slightly different with hypothesis testing. We hypothesize the value for the mean first, if you like, and then we take the sample mean second and think about how far away it is from what we hypothesized. So my advice to you is to make sure that you can do this testing. You know all the steps of this testing procedure for a single mean, which is what I just briefly chatted about. Just one set of data, and you're thinking about where the true blue mu is likely to live. You hypothesize where you think it is, and then really you're looking for evidence that it's not there or thereabouts. All right. You can apply hypothesis testing to the difference between two means. You could apply it to an average difference. Instead of the difference between averages, you can apply it to average difference. And you can apply it to a single variance and two variances as well. Now, we've put this on the kind of hit list, but my advice when you're approaching this material is always get the process for a single mean under your belt, and then you can think that the other tests are just really applying the same ideas. All right, you need to know what a p-value is. You need to know your different errors that can happen, type 1, type 2, and then a brief discussion at the end about parametric versus non-parametric testing. Right, rather than describing what a test is, let's do one, and then we can formulate, a structure of a test afterwards. So a hypothesis test begins with a very strong statement about a population parameter that we can never really observe. Somebody claims, after all, that's what a hypothesis is. Imagine somebody claiming that they know where the true blue mu lives. They know where it is, and they know where it is exactly. So somebody's come along and they've said, I know that the true mean of a distribution is 1%. All right. And the idea is you test that hypothesis. The strong statement about where the parameter is, in this case mu, is referred to as the null hypothesis. So the null here is that the true mean is 1%. There is always an alternative hypothesis, which is the opposite of the null. The alternative would be that mu is not 1%. Okay. Incidentally, in the text, we often give this value that's being hypothesized the letter m naught or mu naught, right? So hypothesis tests always begin with this rather strong statement. I think that mu is 1%. Oh, okay. Now what we do is we take a sample and we think about how likely it is we'd observe that sample under null conditions. If it's too unlikely, we reject the original null hypothesis. That's the idea. So we're going to take a sample of size 101. So that's our n. And what I would say is that there's a significance level of 5%. That's your threshold. If you like, if that's like a small probability, and if we see something less likely than that in our test, in our sample, then we're going to reject the null statement because we've seen something very unlikely, assuming that was true. Okay, so this is like our threshold. When we don't want to see anything less likely than that. If we see something like, and when I say something, what I mean is a sample that is less likely than the significance level under the null condition, then we would reject the null hypothesis. And that's the essence of a test. And actually that rejection, it sounds like a negative thing, but it's actually a very positive thing. Statistically, statisticians are well into rejecting things. They love it. And so, because the idea is the dull null hypothesis is often not very interesting. It's like the base case. It's like, a leaf is green. Oh, is it? Thanks for telling me that. But when you reject that, oh, look, I've got a brown leaf or something like that. It's unusual. So often the null is the boring case, the dull case. I call it the dull hypothesis. And the alternative really represents the thing that we're interested in, the thing that we're kind of hoping for if it's a good thing, or hoping not to see it if it's a bad thing, but we have to test for it. It's often all about the alternative being the existence of something. In this case, maybe 1% is not very interesting, but returning something other than 1% is interesting. Maybe the manager's claimed, oh, my average return is 1%. And you go, okay, let's have a look at a sample of your returns, see if there's evidence to reject that claim. Okay. Now, what we use to conduct our hypothesis test on a single mean is the central limit theorem, which we have already met at a previous module. Okay, the central limit theorem, as you know, says that given a true mean, now we are hypothesizing that the true mean is 1%, all right, but believing that for a moment, the central limit theorem would build a distribution of sample means, a distribution of x bars around that true blue mu. All right, the central limit theorem says when you take an x bar, you're actually sampling from this distribution here, where actually the expected value for x bar, the middle of the distribution, is the true blue mu, which we're hypothesizing to be 1%, and the dispersion of this distribution is the standard error of x bar, which we calculate, usually we calculate it as the observed sample standard deviation S over root n. Now that's all stuff we saw in a previous module. Incidentally, you'll also remember from a previous module that if we use S in the calculation of standard error, which we often do for practical reasons, then you should use a t-distribution for x bar. This implies that the x bar follows actually a t-distribution rather than a perfectly normal distribution, and that's being relayed here. X bar is coming from a t-distribution with n-1 degrees of freedom. Remember that degrees of freedom comment when we speak about t-distributions. There's a different t-distribution for each sample size driven by those degrees of freedom. With a mean, and it's important to appreciate that this is the mean of the sample of x bar, right? This is your expected value for x bar. It means you expect your x bar to be correct. That actually makes it unbiased from an estimator perspective. You expect it to be 1%, but it could be away from 1%. The standard error tells you what the standard miss is likely to be. So first thing you would do here is take a sample and see what x bar you get. We do take a sample and we get an x bar of 1.5. There you go. There's a sample mean. All right. And we also observe a sample standard deviation of 1.4. So what you're going to do now is you're going to think, okay, how far away is that x bar from my true hypothesized mean? Now, we're not saying we believe this yet. We never really do believe it, to be honest. But we're hypothesizing that mu is 1%, and we're thinking, how far away is that thing that we've seen? I mean, in simple terms, in simple absolute terms, we're 0.5% away, right? x bar of 1.5% is 0.5% away from the true blue mu that we've hypothesized. But that's not how we think about distances when we're dealing with statistics. When we think about distances, when we deal with statistics, we think about number of standard errors or number of units of dispersion away from a mean. So what we're really interested in here is how far away, given a significance level of 5%, all right, you'll notice that your significance level of 5% is actually the area in these tails here. These tails are where I'm going to reject. You'll remember that I define the significance level of a test as kind of a threshold. If you see something less likely than 5%, then you will reject that hypothesized mean. So the areas where we could lead to reject, there's actually two of them here. We could see a sample mean that's way too low, or we could see a sample mean that's way too high. So this is what's referred to as a two-tailed test. And that's all driven by the fact that the original null hypothesis says we know exactly where mu is, and therefore when we think to reject that null, we're looking for evidence that mu is either higher or lower than that. Okay, more on that later. So with 5% significance, we know we're dealing with, don't forget that confidence is 1 minus significance. Okay, so we're dealing with a confidence level with this test of 95%. What the central limit theorem says is that 95% of the time, if this is the true mean, 95% of the time you should observe your sample means within about 2 standard errors of this hypothesized mean. Now, when I say about 2, this is where you get your critical distance. You need to know for this distribution here just how many standard errors we need to go either side of the mean to capture 95% of the distribution. Now remember, for a normal distribution, you've learnt that. It's 1.96, isn't it? But for a t-distribution, it's usually a bit higher than that. Remember, well, it will be a bit higher than that. Remember, we've got an n here of 101, so our degrees of freedom that we're using here will be n minus 1, which is 100. So we're interested, when we think about getting a t-value, we're interested in this row. And when we think about the error in one tail, be careful to read what you've got. In each of these tails, you've got 2.5%. It's telling you the distance to go either side of the mean to isolate 2.5% in a single tail, right? So there it is, 1.984. That is the critical t-value we're going to use in our test. We'll just call it 1.98 here. Drop the 4 at the end, but 1.98. That's our critical t-value, okay? And that's really a distance. We're not willing to observe an x bar that's further away than that in terms of standard errors. Because if we do, we see something that's less than, we're looking at something that's less than 5% likely. Okay? So first thing we need to do, or at least what we need to do now, is we need to calculate the standard error of x bar, the sample mean. We do that by simply taking s and dividing by root n. So this is, standard error is s. Don't forget s was 1.4. I work in whole percent. Don't forget, if you're worried about working in when you can work in percent and when you can't, use decimals. You'll be fine. Decimals in, decimals out. If I take 1.4%, the sample standard deviation, divide through by the square root of n, which is 101, I will get 1.4 divide 101 root. So you do it 1.4 divide, type 101 and then just root it, okay, equals 0.1393. So that's the first thing I would do, 0.1393, okay, or in case you're asked that to do that, you already know how to do that, but 0.1393, that'd be the first thing I did here. And what we're interested in is not how far away x bar of 1.5 is from your hypothesized value of 1 in absolute terms. We're thinking how far is that distance in terms of standard errors. And in other words, we're going to take our 0.5%, all right, and we're going to divide by that 0.1393. So you're going to get 3.6 there, okay? So that is a distance. That's how far away your x bar is from your true blue mu that you've hypothesized. Now that 3.6, wow, if that's 2, then that would be 3 and 3.6. It's over here, all right? When I plot on that graph where your X bar has come in, it's way over here. I think the animation on the slide here might put it there, but that's not really scaled properly, all right? The point, though, is that this 3.6 distance, this number of standard errors, is way greater than the critical 1.98 that we weren't willing to tolerate in terms of exceeding. We weren't willing to tolerate a distance that exceeded that, okay? Because we've seen something too unlikely under null conditions. We've seen something that's less than 5% likely, okay? Because of that distance. In other words, we're in the tail. You know, it turns out we're in the right-hand tail here, all right? Or, you know, if you had been in the left-hand tail, you would have rejected in exactly the same manner, okay? So the conclusion here is you reject. We've seen, now this is called a t-statistic of the test, sometimes referred to as a test statistic more generally. We've seen that our test stat is greater than a critical value, all right? The test stat is something you always calculate, 3.6. The critical value is always something that comes from a table because it's telling you about really a threshold in a distribution that we know about. So you've seen a statistic here which is greater than, and these stats are distances. Just remember that. You've seen a distance that's observed that is too far relative to your line in the sand, the distance that you're not willing to observe more than. You're not willing to observe something that's further away than 1.98. So we're going to reject the null here because we've seen something too unlikely. Now importantly, you haven't proved the alternative is true, okay? All you've done is you found strong evidence. You found something very unlikely under null conditions. And like I say, that's how we learn. If I gave you a coin and you flipped it and you got heads, you wouldn't immediately go, this coin always gives heads, would you? You'd start with your null hypothesis that it's a fair coin, and you'd say, that was just noise that I got heads, could have been tails. Flip it again, you get heads again. 2 heads in a row, meh. 3 heads in a row, you kind of go, okay, it's unusual, but not ridiculous. 4 heads in a row, starts to get interested. 5 heads in a row, and now you start thinking about, you've seen something so unlikely, you're going to reject the null hypothesis that the coin was fair. We do it all the time, right? It's just that this hypothesis test here is, it's quite formalized and it involves standard errors and things like that, which makes it a little bit more complex. But we do this in our minds all the time. We assume something that's pretty boring, or the base case, and then we go, oh, look at that. That's not what I thought. So you update what you thought. And the reason it's not what you thought is because it's very unlikely under your null, under your base null assumption. So to lay out the steps of this test, you specify your hypotheses first. In our particular example, the null hypothesis was that we knew that mu was 1%, and the alternative to that is that mu is not 1%. Just a brief word on formulating your test. Your null and your alternative should cover every outcome, right? They should be comprehensive, exhaustive with regards to the value of mu. We can't have any gaps. So yes, mu is either 1 or it's not 1. That covers every eventuality. They're complements of each other, and they cover the whole universe, if you like. What we then do is we select a test statistic, and we think about its distribution. So with the central limit theorem and a single mean, we said that essentially we're going to be sampling, we're going to be working in distances, and those distances are going to be approximately normally distributed. They're going to be t-distributed, okay? And yes, so we're going to be t-distributed around the hypothesized mean of 1. We specify a level of significance. The level of significance is the threshold, the low probability. We're not willing to observe anything less likely than that. If we do, we kick the null out. We say the null's probably, chances are you wouldn't observe something like that under the null conditions, so it's not true. Okay, our test had a significance level of 5%. Notice that 1 minus that gives you the area under the curve, under the bell, all right, outside of the tail, or tails. State the decision rule. In this case, if the test statistic is greater in magnitude than 1.98, notice it doesn't have to be positive, could be negative as well. We're really just saying that if we saw a critical value that's bigger in size than 1.98, either negative or positive, then we reject the null hypothesis. And then we do our sample. We did our sample. We calculated a test statistic of 3.6 when we calculated how far x bar was away from the hypothesized mean of mu naught, which was 1, in terms of the number of standard errors. Okay, and we calculate the standard error along the way, which I explicitly did. We made the decision that that was too far. It's way greater than that critical value of 1.98, so we rejected the null. Now, what we just did there was a two-tailed test. The reason it was a two-tailed test is because there were two rejection zones. And the reason there were two rejection zones is because the original null hypothesis said we know exactly where mu is. So in order to reject that, we're looking for, and you can think of hypothesis testing like that, we're looking to reject. We're looking for an x bar that's either way too low or way too high. Okay. You do, of course, so that's what we just did. It does beg the question, can you get one-tailed tests? And what do they look like? We know a two-tailed test has got equals in the null hypothesis. Can you get one-tailed tests? And yes, you can. You could have a null hypothesis which makes a strong form claim that we know mu is equal to something or it's greater than that level, like here. And if you do make that null hypothesis, the alternative would be, no, that's not true. Mu is less than that value that we've specified. All right, the hypothesized value here, by the way, is 0. All right, 0 is just an example, if you like, an arbitrary choice, or very common choice actually, for mu naught. So a one-tailed test would be mu naught is 0 or greater, and the alternative HA is that mu naught is not equal or greater than 0, so therefore it must be less than 0. Now there's only one rejection zone here, because in order to find evidence for the alternative, which is what you're looking for, means you need to see an x bar that is to the left of the hypothesized mean of 0. Okay, there's only one rejection zone, and be careful, that means all of your significance level, often denoted alpha, all of your significance level goes into one tail. Okay, all right, so your significance level is often called alpha, not to be confused with alpha outperformance active return in performance management, in portfolio management. And with a one-tailed test, as the name suggests, all of your significance goes into one tail. Now be careful with that, because that does have a profound effect on your critical values. Whereas before, if we're working in a normally distributed test statistic, then we know 95% would be 1.96. Your t-values are slightly higher than that. As soon as we go to a one-tailed scenario, to isolate 5% in a single tail, your normal distance there would be 1.65, and your t-values will be slightly higher than that. Okay, you'd have to lift them out of the table like we did before. The mirror image, where we say mu is equal to 0 or less than 0, and the alternative is that actually mu is greater than 0. If you wanted to hypothesize that, then that would be a one-tailed test with the rejection zone in the right-hand side. Notice, with these one-tailed tests, you can find sample means that are a long way away from the hypothesized mean, but still fail to reject, because you'll be a long way away on the wrong side. Like an x bar here is a long way away, but it's not evidence at all that we can kick out the null hypothesis h naught, that mu is greater than or equal to 0. Right? So there's no rejection going on over here, no matter how far away it is. I find that delegates do struggle to formulate tests, and that could be a question in itself. In your exam, with your relatively short questions and short time frame, you're just really picking out stages of a test and demonstrating you can structure tests correctly, and you can talk about them correctly and interpret them correctly. So it's important that you can decide what the hypotheses would be for a particular scenario. A couple of bits of advice for you. Advice number 1, and the most important advice, is that there must always be an equal sign. There's always an equal sign of some description in the null. Okay, if you haven't done that, then you've done it wrong. So, for example, if there's a pure equals sign, then that's a two-tailed test in the null hypothesis. And if there's when I say an equals sign, I don't mean just equals. I mean like greater than or equal to, or less than or equal to. All right, they must always be in the null. Do you notice that? There's an equal sign in the null there. there's an equal sign in the null there. They can't both be in place, right? You do one or the other, and there's an equal sign in the null there. So when you're formulating a test, when you're constructing a test, make sure that there's an equal sign in the null hypothesis. If it's a pure equals, then it's a two-tailed test. Okay. If it's a greater than or equals or a less than or equals, these are both forms of one-tailed test. So let's do a one-tailed test to make sure we're comfortable we can do it. You've got some data for a fund's monthly abnormal returns. Sample mean is 0.35, so that's X bar. Sample standard deviation 1.5, that's S. Sample size 61, that's your N. Your labeling up is very important at this level, by the time you get to this stage, because it helps you to put together the relations that you're going to be using. There's a standard error on the table here for you, and by calculating the standard error as S over root N, something you really need to know, which in this case would be 1.5 over root 61, which is 1.5 divide 61 root. All right, by doing that, 0.192, you also remind yourself that by using S in the standard error of X bar, you are going to be using a t-distribution. Now you're being asked to test the hypothesis that a fund's mean return, and they must be referring to these abnormal returns, right? The fund's mean return level is less than or equal to 0 at the 5% significance level. Now look at the way this has been formulated, all right? We're asking to test the hypothesis that the true mean is less than or equal to 0. So the true mean is less than or equal to 0. Now that's got an equal sign in it, so that would be our null, and we would reject that if we see a mu that's too big, all right? And the area in our rejection tail is 5% in one tail. So one tail test, we are, fingers crossed, we're hoping, somebody said, that abnormal return, this manager, in reality, on average, it's not greater than 0, it's 0 or below. And you're looking to reject that. You're saying, no, I think this isn't just noise, I think this is skill. So we're going to reject the hypothesis that the manager has got 0 abnormal return or lower if we find an X bar big enough. And the X bar, of course, is positive, but is it big enough to rule out it just being noise? That's really the nub of this, this form of testing. So it's a one-tail test with 5% in the right-hand tail. How did I know it was the right-hand tail? Because of the way I formulated the hypotheses. All right, put the equals in the null, and then the greater than equals will come out in the alternative, and that means the rejection zone is on the right. One rejection zone in the right-hand tail. And then so that's what this is telling us here. And then we need to know what this critical distance is. What's the t value for this critical distance where we've isolated 5% in the tail of that t-distribution. Now, if it were a normal distribution, standard normal distribution, the z value for 5% in one tail, it would be 1.65, right? So you know that the t value, we've got decent degrees of freedom here. Degrees of freedom are n-1, 61 minus 1, which is 60. That's a large data set. You know that your t value should be close to, but a little bit bigger than 165. So it's that one. However, if you've got a big table in front of you in the exam, remember they'll give you table extracts should you need them. There's lots of rows, lots of columns. You're going to have to go, okay, we'll take degrees of freedom 60, and we'll look at, it's a one-tail test with 5% in one tail, so we'll look at this column. But this becomes our line in the sand. This is our critical distance, 1.671 standard errors. Just clear that out. All right, 1.671. And so what we need to do now is think how many standard errors is our observed value of 0.35 away from that hypothesized value of 0. Okay, mu0 if you like, 0. How far is that in terms of standard errors? I've already calculated the standard error just by habit to be 0.192. So I can see that this 0.35 divided by 0.192 is not quite 2. It's 1.82. So what have we observed? We've observed something that is 1.82 standard errors to the right of the mean. It is in the rejection zone. All right. So we reject H naught, and we find evidence that the mean monthly abnormal return is greater than 0. Okay. Once again, it all comes back down to that calculated distance being greater than the critical distance from a table, okay, and being in the correct tail as well. You've really got to, don't step away from this too much and try and just do it with your eyes shut. You've really got to keep looking at what you're doing and thinking about what you're doing once you've formulated your hypotheses correctly here. Now, you're never 100% sure about any statistical conclusion that you come to. And the fact is, when you do come to a conclusion like this, reject the null, you might not be right. You could have rejected a true null. The other mistake that you could make, of course, is that you could fail to reject a false null. Okay, so when we're talking about the errors that can happen in statistical testing, make sure you focus on there's only 2 errors you could make, and you can't make them both in the same test. The way to think about this is you come to a conclusion, like reject the null. Okay, great. Now, hopefully that's the right thing to do. Hopefully the null's false. However, there is a chance that you may have made an error. And if you reject the null, H naught, when actually it's true, that's referred to as a type 1 error. Okay. The other type of error that you could make is where you fail to reject something that was false. Okay. Remember, failing to reject something that's true is not an error. But if you do a statistical test and you fail to reject, and yet actually the null was false, which you can never really know, that's referred to as a type 2 error. Okay. Now, these are quite difficult to remember, but what I would recommend is that you just think, look, there's only 2 types of errors, type 1, type 2. You make these errors based on the result of your test. So do your test and you either reject, notice I've circled that C there, or you fail to reject the null. Now, failing to reject the null, you never prove that the null is true. You never do that. That's bad logic. But you are kind of accepting it if you fail to reject it. Now, there's 2 C's in accept, and that reminds you that failing to reject the null, accepting it, when actually it's false, that's a type 2 error. Rejecting the null, when actually it's true, there's 1 C in reject, that's a type 1 error. Okay. Now, when it comes to chances of actually making these errors, the probability of a type 1 error is actually very straightforward. It's the significance level of the test. You remember that small number, say 5%? Yeah, that's actually the probability that the null was true all along, but you accidentally rejected it. If you think about it, we do assume, really, when we do the test that the null is true, because we build our whole test around the fact that we temporarily believe, essentially, that the mean is there, the hypothesized mean. We temporarily believe it. Now, if it is actually there, what we believe and what's true, different things, if we believe it's there and it is there, then this is the true distribution of sample means that we're sampling from. However, we're still going to be unlucky, aren't we? By definition, you are going to be in the tail, even when the null is true, right? You've hypothesized the correct mean. You are still going to get an outlier sample in this tail 5% of the time. By definition, that's going to happen. So actually that significance level, whilst I defined it as like a threshold, and I'm not willing to observe anything less likely than that under null conditions, actually when the null is true, you do still observe this extreme 5% of the distribution, and you accidentally reject a true null. You're not always rejecting true nulls, all right? 95% of the time when the null is true, you get a sample mean that's within this range, and you fail to reject correctly the true null. But when the null is true, conditioning on the null being true, 5% of the time you will still see outlier samples. Maybe there's a lot of noise in the sample, and you'll be in the tails, and you will incorrectly reject a true null. Rejected's got 1C, type 1 error. So that's the probability of a type 1 error. The probability of a type 2 error is not trivial and beyond the CFA curriculum. If you think about it, the probability of a type 2 error where you accept, 2 C's in accept, or you fail to reject, technically, a null that was false, Well, the likelihood of this happening is you assume it's true, and then you sit in the fail to reject zone, all right? But you're actually sampling from a different distribution, which is centered around the true mean, which is not the mean that you've hypothesized. So that's quite tricky. You've got two distributions intersecting there. It's quite tricky to estimate the probability of a type 2 error. However, it is type 2 errors that statisticians don't like, because a type 2 error is a real missed opportunity. Don't forget that statisticians they celebrate rejection, right? The alternative hypothesis is often the one that's very interesting compared to the dull null. So when they miss an opportunity to reject the dull null and they accept the dull null and they think nothing's there when something is there, that is not good news for statisticians. They don't like it. So what statisticians will do is they'll design a test with the highest power possible, because a high power test has got a very low probability of making a type 2 error, sometimes referred to as a beta error, okay? Or the probability of a type 2 error is referred to as beta. So if the power of the test is high, that's a good thing. It means we're very likely to reject a null when it's false. Along comes a false null and we see it, which is good news. And that ties in, that's intuitive, isn't it? Strong power, means we haven't got a very big probability of making the dreaded type 2 error, which statisticians don't like. There's an example sitting on the slide here, tucked away. When it comes to the judicial system, of course, everyone's innocent until proven guilty. All right, and a type 1 error would be where you reject that null and you find someone guilty when actually they're not guilty. All right, this is the null here. So that's a tragedy. That's a miscarriage of justice. You're locking up an innocent person there. The other type of error is where you fail to convict a guilty party. Now that's more sinister, isn't it? They get away with it. So it's another miscarriage of justice, but they're out there. The murderer's still out there and they're free to carry on their sinister, plans or whatever. So that's, once again, coming through, using that as an example, it's the type 2 error. Whilst locking up an innocent person is a miscarriage of justice and a tragedy, failing to lock up a dangerous person is a miscarriage of justice and quite sinister. Maybe you can take that away to remember which type of error the statisticians don't like. It's the type 2 error. Okay, now when we do statistical testing, often people sort of say, why do we bother with distances? If we reject the null when we see something less likely than the significance level of the test, why don't we just calculate the likelihood of observing our sample under null conditions, and if it's less than the significance level, we reject? Well, I say, statisticians do that. It's called the p-value, the probability of observing our sample under null conditions, all right? Or something more extreme, that's called the p-value. Just think it's the probability of observing our sample under the null conditions. And yes, if that's like 2%, all right, and our significance level is 5%, then yes, we've seen something too unlikely, and therefore we reject the null. Don't forget, it's always the null you're rejecting. Just to picture what's going on, if we had a one-tailed test, we might hypothesize a mean here, like a true mean here, obviously. Actually, if we've got a one-tailed test, we hypothesize that the true mean is here or it's less than there. So if you like, mu is less than or equal to mu naught. That gives us a rejection zone here. And with a one-tailed test, all of the alpha of, say, 5% will be in that one tail. To picture what the p-value looks like, it is the area outside our sample mean. So if we observe a sample mean here, the area outside of this, just in that tail there, is the p-value, okay, of what we've observed. And by definition, if the p-value, the area outside our sample mean, what we've observed, is less than the significance level, say 5%, then we must be in the tail. Okay, so that's, that's how to picture it. The area outside of what you observe, if it's smaller than the tail, you must be in the tail. And that's what we're saying here. P-value of, say, 2%, less than significance level of 5% means we're in the tail. Okay. A less helpful definition of p-value is that it's the smallest level of significance, alpha, at which the null can be rejected given our sample. So if you think about it, if we did get a p-value of Yeah, we'll go with 2.13%. I think that's the area outside of what we observed. Well, if alpha's greater than that, say 5%, we would reject, wouldn't we? Because we're in the tail. If alpha was at 3%, say here, the area in the tail was 3% outside of that, then we'd still reject, wouldn't we? It's only when alpha falls to actually the p-value that we stop rejecting. We couldn't reject if we used an alpha or a significance level of 1%, because there our p-value would be too big. It wouldn't be lower than the significance level, which is our threshold, where we decide we've seen something too unlikely for the null to be true. Right, now what I'd like to do actually in this masterclass is just kind of call a timeout, because whenever, if there'll be many of you out there, if you're fine with statistical testing, you've seen it before, or everything just seems to be landing right in your pocket, go ahead, jog on, right? But there'll be some people out there that'll be thinking there's quite a lot to take in here, and maybe I need to digest this, maybe I need to do some questions, check my understanding, and tweak my understanding, go back and read it again. So for those people that are at that stage, or in that kind of state, I would advise that you don't go on and get beaten up by what I would refer to as the higher order tests. These are tests of, say, the differences between means, or the average difference between means, and test of variances and things like that. If you're meeting statistical testing for the first time and it's a bit of a steep gradient, then pause here, go back and get the material under your belt first before you carry on. Okay, that's my advice from a learning perspective. For those that do want to carry on, and for once people do carry on, what we're going to see next is the hypothesis test idea, right? That is, state your hypotheses, calculate a test statistic, compare it to a critical value, make a decision, that sort of idea, applied to different types of statistics for different types of parameters. So let's think about testing a hypothesis about the difference between two different means of different distributions. Here we're going to follow exactly the same logic as before, all right? We're going to make a hypothesis this time, though, not about a single mean, but about the difference between two means. So there must be two different distributions here. Now, you'll remember when we tested a single mean that the test statistic was simply how far away our observed mean was from a hypothesized mean, okay, in terms of standard errors of that single mean, yeah, where standard error, by the way, was S over root n. So we've seen that a lot now. You'll notice that when we calculate our test statistic, when we've got two different distributions and we're thinking about the difference, the true difference between mu1 and mu2, you'll notice there's the same shape here. It's what we observe. We've got two samples now, one from the first distribution, x bar 1, one from the second distribution, x bar 2. And then we think about how far that difference is away from a hypothesized difference. Often we may hypothesize that a difference is 0, actually. In other words, the means are the same. That's a very common hypothesis, all right? But it doesn't have to be that. But we've come up with some. It's usually the case that we are hypothesizing that the true means are the same. And then underneath the, on the denominator here, we have the standard error of x bar 1 minus x bar 2. All right, it's how much standard deviation there is in this difference between means, okay? You'll notice it does very much, if I view this standard error, by the way, as the square root of s squared over n, you'll notice it very much follows that shape. It is in fact sp squared over n1, where n1 is the size of the first sample from the first distribution that you got that mean from, and n2 analogously is the size of the second sample that you got from the second distribution. So we can see that's a standard error type shape, all right, s squared over n. The question is, what is sp squared? What is that? Well, that's a pooled variance calculation. Being a pooled variance, what it's doing is it's throwing both samples together and it's trying to calculate a variance using all of that data. Okay, so in here you see the sample variance for the first sample and the sample variance for the second sample, and you see they've been multiplied by their denominators. Now, if you think about it, if I just think about S1 squared, what is that? That's the sum of squared deviations from the mean. I won't use, Greek letters because they just get in the way. But as we know from our basic stats, S1 squared is the sum of deviations of the first sample from its mean squared divided by N1 minus 1. That's called the degrees of freedom of that first sample. So when we multiply through by N1 minus 1, what we get is just the sum of the squared deviations from the first sample. That's what all of this is. It's the sum of the squared deviations from the first sample, right? And this, therefore, all of this must be the sum of the squared, this over here must be the sum of the squared deviations from the second sample. All right, so all we're doing on that numerator is just adding up all of the squared deviations from both samples. Great. Then we're going to divide through by the total number of degrees of freedom. Now you've got N1 minus 1 degrees of freedom for the first sample and N2 minus 1 degrees of freedom for the second sample. If you add those up, you'll get N1 plus N2 minus 2, right? So yes, it looks ugly as sin. And to be honest, the reward, the return on your investment for that pooled variance for the exam is it's probably negative when you consider opportunity cost of picking up marks elsewhere. So don't fret. And whatever you do, think about that timeout I called about 5 minutes ago. Whatever you do, don't let this higher order stuff stop you from mastering the basics of hypothesis testing and passing very healthily this section of the exam. Okay. However, this SP squared, that's essentially a variance that goes, sample variance, which goes here divided by M1 to represent the standard error of the first sample. And we're going to add, it's technically that's the variance coming from the first sample. All right. And this is the variance coming from the second sample. And then you take the square root and you'll get back to the standard error coming from the difference between the means. In other words, from both samples. Okay. Let's apply it and make sure it adds up. This is a CFA Institute example. Suppose we want to test whether the returns of ACE high yield total return index shown below are different. Now, when they say we're going to test whether returns are different, you need to start thinking, oh, okay, we'll hypothesize that the returns are the same. Don't forget, your null hypothesis must always have an equals in it. So mu1 minus mu2 is 0 here. And then we reject that if we find evidence that they're different, they're non-zero. So we're testing to find any evidence that these means are different. When they say returns, they mean mean return. Okay. For these different periods. Look at this, period 1, period 2. So there's your first. Now, what you're looking at here is sample data. You're looking at, I'll label that one X bar 1. All right. That one's X bar 1. And that's X bar 2, your sample means. That there is S1, that's S2. And that's the sample you did for the first period, N1. And that's the sample you did for the second period, N2. So do the test basically. Do you find any evidence for a difference between the mean daily returns in these two periods? There's your significance level of the test. Now remember, it's exactly the same process as what we said for a single mean. It's just the application that differs, and you've got this pooled variance going on with the standard error. So first up, state the hypotheses. I've already spoiled that one. Mu1 equals mu2, or equivalently, mu1 minus mu2 is 0. Same thing. That's the null. The opposite to that is that the difference is non-zero. You could state that as mu1 is not equal to mu2. Now, the appropriate test statistic, it is still a t-distribution. The difference between these sample means is still, you're still sampling from a t-distribution. Okay, so we're going to use t-statistics with N1, which is 445, plus N2 minus 2 degrees of freedom. That's 1,302 degrees of freedom. That's so many degrees of freedom. We're going to be looking at pretty much a normal distribution. Okay. Your critical value, yeah, so in other words, t-values are going to tend towards z values, our well-known z values for a normal distribution. And by the way, we've got two tails here. How do we know we've got two tails? It's because of the way the hypotheses are set up. Given that we've hypothesized an exact value for the difference between the means, we only need to find a very negative value for the difference or a very positive value for the difference for us to reject. So there's two tails. It's that actually not equals to sign that tells us it's a two-tailed test. Okay, and we know that for a two-tailed test, 95% confidence, we need to go 1.96 standard errors in this case. And we're assuming normality because our sample size is so big, our combined sample is so big. We need to go 1.96 standard errors either side of the hypothesized mean to isolate 95% of the distribution and isolate 2.5% in each tail. Okay, so that's all following exactly what we did for a single mean. When it comes to calculating the test statistic, there's a little bit more heavy lifting going on with two distributions. And we're looking at the difference between means because we use the pooled variance. So the pooled variance, which is S squared P, you'll remember that we calculate it by taking the total sum of squares observed in our two samples. That there must be n1 minus 1 multiplied by S1 squared. Just check. Those numbers, yeah, that's right. We're working in whole percent. Okay, so that's scaling the first, really the first variance up to just look at squared deviations. This must be n2 minus 1 multiplied by s2 squared. That's scaling up the second variance to just go back to the squared deviations. And then we're dividing through by n1 plus n2 minus 2. Okay, that comes out at 0.1330. So take your time with that calculation. We did discuss it before. That means your t-stat is going to be your observed difference in means, x bar 1 minus x bar 2. Right? That's what's in those brackets. That's what's in the brackets there. So we've gone with decimals now. No, we haven't. Apologies. These numbers are very small. Okay. So they look like decimals. Just be careful there. They look like decimals, but they're not. They're still whole percentages. Okay. Which is consistent with what we were doing. These were whole percentages before, aren't they? So that's x bar 1 minus x bar 2. That's the hypothesized difference. Don't forget that the hypothesis, the null hypothesis, was that mu1 was equal to mu2. So the hypothesized difference is 0. And then we're dividing through by pooled variance divided by n1 plus pooled variance divided by n2. And don't forget to take the square root of all that on the denominator to get back to a standard error rather than using a variance term. Now that comes out at 0.3. Now look, to be honest, you're probably going to be reading this stuff rather than doing it in the exam. And like I said in the timeout, don't let this heavier, uglier stuff stop you from understanding the basics of hypothesis testing. Because you've got a test stat here. You can answer now what we do with our decision. If your test statistic, your test distance is only 0.3 and you've got a critical value of 1.96, you haven't reached the reject zones. You're still in the fail to reject zones. So that's your conclusion. You failed to reject the null hypothesis that the two means in reality are actually the same. Okay, so the test we've just done assumes that the two samples are actually independent of each other. And what we mean by that is there's no direct link between any member of the first sample and any member of the second sample. That was tucked away right at the start of the test, and I may well have jumped over it. There you go, 4 independent samples from different distributions. There's no direct link in this example here. There's no direct link between, say, we've got period 1 and period 2. They're clearly quite long periods, right? The second period is twice as long, almost, as the first period. And there's no direct link between the first element of period 1 and the first element of period 2. They're independent to each other. Now, if you've got samples which actually are dependent on each other, in other words, they're related to each other in some way, then you don't test difference between means to see if the samples are different. Actually, you test the mean difference, which is a slightly altered approach. And let me give you an example here so that we get a bit more colour. imagine if you were to make the hypothesis that this course doesn't work, right? You might take a sample of people that haven't taken the course and see how they score in a test, and then they take this course, and then you take a sample again of how they score in a test. Okay, so it's like a before and after. That's the way to think about it. That's how this one is often applied. It's like a before a course versus after a course, or before a drug is applied versus after a drug is applied. These two samples, there is a deliberate and important link between the first observation of the first sample and the first observation of the second sample, because we're really testing whether we've made a difference to that observation. And we're looking for evidence that the average difference is non-zero. So let's take 10 people, for example, so sample size 10. Let's measure their scores. You'll get, X1, X2, X3 before they take the course, X10. Then they take the course or they take the drug, and then you measure their scores or whatever the drug's designed to do, how much they sleep or, how much energy they've got, whatever. And you take another sample, say Y1, Y2, Y3 to Y10. Now, what makes these two samples depend on each other is that X1 is the same person as Y1. The difference, though, is something's changed. Their environment has changed. Okay? So you would calculate here, for these two samples, you'd calculate D1, it's the difference between X1 and Y1. All right? You might want to, if this person scored 50% and then they took this course and they scored 60%, then you'd say D1 would be, say, after minus before, D1 would be 10, for example, and so on. Look at D2, D3, D4, all the way down to D10. And then you're just going to conduct a hypothesis test on a single mean for these differences, D1 to D10. All right, you'll look at what your sample mean difference is versus a hypothesized mean difference, which is often 0, because the dull null is that the course doesn't work, and then you're going to compare that to the standard error of these differences. And the standard error of these differences is calculated in exactly the same way as the standard error of x bar, the sample mean from before. Take its sample standard deviation, divide by the square root of n. N is 10 here. And it's the same test, a t-test with n minus 1 degrees of freedom. This is exactly the same test as what we did for a single mean when we went x bar minus hypothesized mean divided by standard error. All right, it's exactly the same as that. So actually nothing new there. But keep an eye out for the application when you're looking at the difference, the average difference that some sort of change in environment has on essentially a sample, then you must test the mean difference rather than test the difference in means, okay? Because the two samples are dependent upon each other. Right, on now to a different type of test, and that is testing variances. The process is still the same. Variance, of course, is how much squared deviation we've got in our distribution. The hypothesis, of course, would relate to a hypothesized level for the overall variance, the true blue variance of the distribution. You might say, I think that variance is, if I go in sort of squared percent terms, I might, whole percent terms, variance is 400. The alternative hypothesis would be that the variance is not 400. Okay, that would be a two-tailed test. Now, you wouldn't expect variance and a sample variance to be normally distributed, would you? Because variance is a squared distance, so it can't go below 0. So that's why when we calculate a test statistic and we want to see how big, look at that on the top there, we've got our sample variance. All right, we can just look at our sample and get that. That's sample variance. And we're scaling up by n minus 1. That's the degrees of freedom of our data. So all of this stuff on the top here is really just the sum, once again, the sum of the squared deviations in our sample variance, right? We're thinking how big is that versus the hypothesized variance, which in this case would be 400. And the idea is, of course, if the sum of squared deviations is significantly bigger than the hypothesized variance, then chances are we haven't hypothesized the correct variance. And if it's significantly smaller as well, then chances are we haven't hypothesized the correct variance, and so we reject. The test here would actually be coming from not a symmetrical t or normal distribution, but from what's called a chi-square distribution, all right, which is actually positively skewed and bounded below by 0. Like I say, you wouldn't expect variance squared difference squared deviations to go below 0. So that's what a chi-square distribution looks like. You would follow the same process as before. All right, this is your test stat that you calculate, and then you compare it to a critical value given to you in a table with n-1 degrees of freedom, because there's one data set here, and we've lost 1 degree of freedom because we've calculated the sample variance in our test. Okay, so if you observe a test statistic that is in this zone for a two-tailed test, which this is here, you'd fail to reject. If you observe a test statistic that's greater than the higher critical value, you'd reject. And if it's greater than the lower critical value, you'd reject. Just need to keep an eye on what you're doing and acknowledge that there's no symmetry here with like a normal or T distribution. So let's do it. A fund manager has a mandate specifying that monthly volatility should be a maximum of 2%. Okay, that's a crucial figure. Since inception 3 years ago, the manager has achieved a mean monthly return of 1%. Not massively interesting now. This is, though, a monthly standard deviation of 2.3%. So let's label that S squared. Now you can see how important labeling is. I almost mislabeled that. When you label, like I did just there real time, you second check that your label's correct, just automatically. And I don't label that S squared at all, do I? Very important that I just labeled that S. Okay. Test whether this data implies that the true volatility of the manager breaches the mandate. When would they breach the mandate? They would breach the mandate if true volatility is greater than 2%. Okay, so this is what we're looking for evidence for. All right, notice there's no equals sign in that, so it's an alternative hypothesis. The alternative hypothesis is we're looking for evidence that true volatility is greater than the limit, 2%, which, by the way, translates into a variance comment that we're looking as to whether sigma squared is greater than 4%. The null, which is where there's nothing to worry about, there's nothing, that's where true variance is less than or equal to 4%. We're looking for evidence of this, and that becomes our alternative hypothesis. If you're still struggling to construct your hypotheses, then just think about that rule about the equals sign. One of the hypotheses is going to be that the standard deviation is greater than 2. Greater than hasn't got an equal sign in, so that has to be the alternative. If you use that rule does you pretty well. So actually, all we need now really is to calculate the test statistic. You are going to have to remember this one. It does come from kind of undergraduate level statistics that we don't know about. Why that test statistic follows a chi-squared distribution. We're just, if you like, we're consumers of this. We're not producers of this or provers of. We don't prove this. We just use it. We've got a one-tailed test here. We've already agreed that they are the hypotheses. We're going to reject H0. There's only one tail, so with our chi-square distribution, we're only going to reject if we're in the upper tail, if our observed test statistic is too big, and with all of the significance level in one tail, and we must be told a significance level somewhere, there it is, 5%. With all of that in one tail, we need to find out what the critical value is from a table. Don't forget, critical values always come from a table. Okay, that's a rule you can hang your hat on. Critical values come from a table. Test statistics come from a calculation. We need to find out what the critical value is for n-1 degrees of freedom. N here is 36. Okay, how did we get that? Well, we looked at monthly data, all right, and we looked at it over 3 years, all right, since inception 3 years ago. So that's a little bit of a smoke screen being thrown up by the question. 3. Some people might say n is 3, but it's not. It's 3 years worth of months, and there's 12 months in a year. So our sample size is 36, 3 lots of 12 months. n-1 is 35 degrees of freedom. Here is a chi-square table. All right, we're going to use 35 degrees of freedom, so we're interested in that row, and we want the probability in the right-hand tail to be 5% because it's a one-tailed test, so we're interested in that column. So our critical value pops out as 49.802. Let's just call it 4980. And now we calculate our test statistic. You need to know that formula. All right, the test statistic is n-1 lots of s squared, where s is the sample standard deviation. You can work in whole percent. We're going to go 35 times 2.3 squared. Now, I labeled it s a long time ago. There it is, 2.3. Okay, and we divide that by the hypothesized variance of 2 squared, and we get 46.29. Now remember, our critical value from the table was a bit higher than that, wasn't it? 49.8. Yep, 49.8. So we've seen something that's not big enough, not quite big enough to get into the reject zone. So we say there's no evidence that mean monthly returns are breaching the mandate. They're greater than 2%. To picture what's going on, we've got a critical line in the sand of 49.80, and we've observed something that has a test statistic of 46.29. So nearly, but actually not quite. All right, and we fail to reject. Okay, great. Now, final test is actually a really straightforward one, and that is testing the difference between variances, or testing two variances together. So here our hypotheses will relate to the ratio of sigma 1 squared and sigma 2 squared, the ratio of two variances, true blue. Now the test statistic here couldn't be more straightforward. You'd guess it almost. You know, we're just looking at the ratio of the sample variances. That gives us our test statistic. It follows what's called an F distribution, which is similar to a chi-square distribution in that it's bounded below by 0. It's non-negative and it's got positive skew. However, it is a different distribution, and it's got 2 degrees of freedom, one for the numerator, which we know to be n1 minus 1, and one for the denominator, which we know to be n2 minus 1. So this is actually, to finish up, this is actually a really straightforward test. Let's have a look at a CFA Institute example. You are investigating whether the population of returns on a stock market index changed after a change in market regulation. First 418 weeks occurred before, and then another 418 weeks afterwards. So this is giving us our sample size. If we're looking at weekly data, sample sizes, they're actually the same. You've got an N1 of 418 and an N2 of 418. Okay, you gather data, all right, before and after. There's your alpha, 5% significance there. Okay, and then right, mean weekly return. Not massively interested in that, to be honest. We're more interested in this variance of returns. There's S1 squared and there is S2 squared. They ask, are the variance of returns different? Now, that's a bit of a strong form statement. They should really say, is there any evidence that the variance of returns are different with 5% significance? In other words, do a test of the dull null that they're the same. All right. In other words, sigma squared before is the same as sigma squared after, and look for evidence of the alternative that they're different. Okay. The appropriate test statistic is going to be an F statistic. You just need to associate that with testing the difference between variances. All right. Chi-square is nice and easy to remember for one variance, isn't it? Because variance is a square. Chi-square. All right. And then the F distribution, you kind of go, there's one more, isn't there? And it's the final one, right? The F distribution. Okay. So F distribution, n1 minus 1 degrees of freedom on the numerator, n2 minus 1 degrees of freedom on the denominator, and then we find our critical value. You go off and look at an F table. They'll give you an extract. Look up these degrees of freedom. Look for 5% with 2 tails here because of that hypothesis. All right, there's 2 tails. You could reject because your stats too low. You could reject because your test stats too high. 2 tails. You'll get told there's critical values from the table of this one on the left-hand side, 0.82512, and this one on the right-hand side, 1.21194. That will come. Remember, your critical values always come out the table. So now all there is left to do is to calculate your test statistic and compare it to your critical values like we do in every other test. So take the ratio of your variances, your sample variances. Remember, Your sample variances were given in the table, 4.644, 3.919. They were given to us here. We did label them earlier on, okay? And so you can compare those and you get 1.185. Now, does that fall outside of the fail to reject zone? The answer is no. It does not. As we drew earlier, the fail to reject zone starts here, 0.82512, and ends there. All right, 1.21194. And we've observed a test statistic that is inside it. It's about here. So we failed to reject the null. You always remember the rejection zones are the tails or the single tail in a one-tailed test. Now, everything we've been doing so far, now that's the final test we're going to look at. Everything we've been doing so far has been parametric because it's relied on assumptions about population distributions, population parameters, and how they behave. T-test of means, Z-test of means, of course, when we've got enough data, we know the population standard deviation. F-test for comparing differences between variances, as we've just seen. These are all looking at the parameters of population. They're looking at means, variances, and so on. You do get non-parametric tests. Non-parametric tests don't revolve around the parameters of a distribution, like mean variance or even things like skew, kurtosis, or covariance, correlation. They focus on other features of distributions. Your curriculum mentions runs tests, like how long a run we get in positive returns, then negative returns, or returns that are above and below the means, and seeing if there's any patterns there. That's not your usual mean variance. That's really looking for patterns in data. And you do get tests based on ranks rather than values. So, of course, the mean is a mean value. A rank looks at whether rankings are similar in certain time periods, for example, to see if there's a relationship. So these aren't focusing on things like mu, sigma. They're focusing on other features of distributions that maybe are a little bit more left field and have less established statistical theory. In fact, the next module looks at some non-parametric tests, so this is a segue into that. All right, well, look, that does complete this module. I think I'll just, at the end of this module, I will just repeat the advice that I gave about taking the time out after you've looked at testing a single mean and getting really comfortable with that before you go on and get beaten up with those higher order tests. Chances are you can do very well in the exam if you're very solid on your statistics, your quants in general, and you know the basics of hypothesis testing. Okay, so my message to you here is don't, let your confidence be knocked, and don't think you're going to do poorly in quants if those higher order tests don't immediately fall into the pocket. Okay, get the test of a single mean down, and the higher order stuff, pick up the marks that you need there, and you'll do absolutely fine.